Heejun from Yonsei University. Let me present our work, automated P&ID compliance checking via LLM-based code generation. P&IDs are among the most critical plant design documents, and their quality directly affects safety and efficiency. But checking the line numbering schema and the required design attributes is still done by hand. This is time-consuming, error-prone, and very costly. So we target to foundational checks whether the numbering rules appear correctly and whether each drawing includes the essential design information. Let's look at the prior works. Image-based computer vision recognizes symbols very well, but it interprets an image probabilistically. Vision LLMs look like a natural fit. They can turn natural language rules into checks. The risk is letting the model do the verification itself. Hallucination and non-deterministic outputs are unacceptable when the same drawing must give the same verdict every time. So the model only writes the code. Following recent neurosymbolic work, the LLM formalizes the rule, and a symbolic engine gives the verdict, and the checking needs an input we can parse deterministically. We set two research questions. The first question asks whether this limit of LLM-based review is real. The second question asks how LLM only writes the code and the check runs on the CAD data itself. So where does input come from? Let me show you how P&IDs move in the practice. In plant projects, basic design and construction design are often done by different companies. In that setting, CAD files move around. The construction contractor asks the designer for the CAD files occasionally to fix the errors directly. So reviewing the CAD file is a part of the contractor's work. Our goal is to automate this task. We compare both on the same drawing. Drawing A104 was obtained in both formats, and both are scored with the same ground truth and the same metrics. In approach A, a vision LLM reads the drawing as a PDF format from CAD file directly. We use Cloud Sonnet 4.5 as a representative baseline. When extraction fails, the model reviews its own errors, applies a fix, and run again. We repeat this loop 3 times and measure the improvements. Approach B is our method. It parses the DX file format from CAD files directly. And let me explain the detail from the next slides. Approach B is a separation of concerns. The workflow has 3 parts. First, we extract the engineering object directly from the DXF file. Then the LLM does 2 things. It formalizes each natural language rule into a FOL expression, and it generates the Python verification code from the logic. From there, the checking itself runs deterministically. The same drawing always get the same result. Approach B rule verification is carried out by 2 checkers. Checker 1 checks the numbering format. Checker 2 checks the design rules. Let's look at checker 1 first. It verifies whether each line number follows the schema defined in the symbol and legend datasheet. Take the line number on the screen. It decomposes into 6 fields: pipe size, service code, line number, piping specification, installation type, and tracing type. Checker 1 validates each field against its prescribed format and values. Checker 2 deals with the meaning of design rules. Follow the flow of the bottom. A rule starts in natural language. A machine cannot evaluate that sentence directly. So the rule is formalized into a first-order logic expression. Then the logic is converted into executable Python code. The check itself runs deterministically. Together, the 2 checkers perform 557 checks in total. Let me start with the rule set. In this study, we target a total of 9 design rules. We organize them into 2 classes by what each check does. Classes Numbering rules check whether each ID follows the standard schema. Essential information rule check whether the required information is present. For the data, we used 7 test P&ID drawings from an industrial plant project. The first 3 drawings, 101 to 103, are the standard drawings. They define the drawing conventions, the numbering schema, and the abbreviation codes used across the project. Drawing 107 to 107 are the actual P&IDs, and each of them lets us verify all 9 of our target rules. To keep the comparison fair, drawing A104 was parsed into both PDF and DXF formats. Both approaches read the same drawings. The parser was built on A104 only. Then it was applied to A105 through A107 without any modification. The ground truth was built by hand and cross-checked against the original design specifications. We report F1 score for both approaches. Now let's see the results. Let's look at the image-based LLM first. It handled drawing information and GIMOT, both at 100% F1. But it struggled badly on the harder categories, lines at 48% and process streams at about 71%, giving an overall F1 score of only 55.9%. And this did not improve. We ran 3 iterations with post-processing and error pattern correction, and the scores stayed flat. The failure was systematic. Text misrecognition in low contrast regions, wrong spatial associations, confusion among overlapping elements, and loss of attributes that are implied rather than written as text. These are structural limits of image-based reading. Our DXF-based method tells a different story. Drawing information, equipment, and lines all reached 100% F1 across all 4 drawings. The only draw was in process stream on A107 drawing, which pulled the overall F1 to 97.5%. On the verification side, all 587 rule checked passed with 0 violations. There were 13 warnings, but those flagged incomplete source data, such as unregistered material codes rather than code failures. The one weak spot, A107 process streams, came entirely from streams that lacked explicit from and to boundary markers in the source file, which is a known limitation of text-based spatial matching. Putting them side by side, the contrast makes clear. To summarize, our contribution is a neurosymbolic design. The LLM only writes code, and a symbolic engine gives every verdict. So results are deterministic and reproducible. By parsing the original DXF instead of an image, we avoid probabilistically misreads, and across 587 rule checks, we reached 97.5% overall F1 with 0 violations. It also has limits, 6 of them listed here: rule coverage, level-dependent connectivity, single project scope, the fidelity of LLM-generated logic, untested violation detection, and DXF dependency. We address each of these in future work. Thank you for listening.